Thank you very much. I work with a company called Geometrics, and we've been in existence since 1969. And we spun off from a medical electronics company in Palo Alto, and we've been building magnetometers for 40 some odd years. We also build seismographs. We also build electromagnetic equipment. So what I'm here to talk about today, though, is some sort of revolutionary advances that have happened quite recently. These are technological changes which we believe will affect everyone on some level or another. And that's a broad statement, but we feel that the advances that we are seeing in microfabrication, extreme miniaturization of geophysical sensors can make a substantial difference in the way in which the world is analyzed, and security, and a whole raft of other applications. So I'm going to talk today specifically about magnetometers, but frankly the micro-miniaturization aspect and the interconnectivity, which means that sensors are strung together with ever faster and smaller and lighter and lower power networks, is happening on a variety of fronts for us. So I'm going to talk about a specific project that we've been involved in for 4 or 5 years, and it does have some relationship to what I believe people should be studying in their education for application of geophysical instrumentation. So I want to talk about how we find metals. And of course, one of the primary methods is airborne. We have here a helicopter system, and it has multiple sensors on it. So this is actually an airborne magnetic gradiometer. Now, why would they put more than one sensor in the air, particularly when they're probably flying at between 100 and 200 meters altitude? The reason is that the sensors are they get a fine enough resolution of the magnetic field that even at 100 meters we are able to see gradients over the range of a few meters. So these sensors are extremely sensitive and are able to help the interpretation. Here's another example. We see here a magnetometer, and then lower down is a transient EM loop. So this is approximately 45 meters in diameter. So these are large impulse type systems where a magnetic pulse is put into the ground, and then they look for the ring down of the electromagnetic signal in the conductor. But they must have the magnetometer as part of the system in order to help interpret what they're seeing. Recently, the magnetometer has been lowered to closer to the electromagnetic ring. The reason is that they want to get higher fidelity, higher resolution of that magnetic signature. One of the issues having to do with that, however, is that when you put a magnetometer close to a high impulse electromagnet of this nature, you tend to knock it off lock. And some of the things I'm going to talk about today have much improved that. We also have fixed-wing aircraft. And even back in the day, this is a rather old aircraft that Geometrics used to fly, but we had 3 sensors, one in the tail and one on each wing. And again, the rationale here is that we could actually see out to the left and to the right of the flight line. We can actually determine something about the slope of the magnetic field and therefore get a better analysis of the geologic structure. So what's driving this exploration? Well, I thought I would grab a couple of plots of dollar values of metals. And here we see that gold is up 500% in 15 years. Not all prices of metals, of course, are driven by let's say, sane decisions, but obviously there can be political, geopolitical, and economic reasons why certain metals become more valuable, but just an increase of 5 times in 15 years is impressive. How about base metals? course, magnetometers does not detect copper directly, but base metal exploration is part of the magnetic survey regime. And we see that the price is up, again, 5 times in 10 years. What drives this? Well, we know that electrification of rural communities is a big part of that. How about iron? Iron is a huge a source of material, of course, for economic exploration, growth. And so here we see it's up by a factor of 8 over 10 years. Now, we know what's really driving this. This is a lot of construction in third world countries, India, particularly China. But this shows that the price of these metals is driving the primary exploration efforts. And in fact, I have a graph here of just iron ore requirements in China. It's a little bit dated. It's a couple years old, but you see that back in 2005, they were projecting a certain slope, and then a few years later, the slope had increased dramatically. I know that it's leveled out a little bit with the world economic situation in the last couple of years, but still, again, an impressive increase in demand. So conventional airborne exploration programs, a few notes about them. They're expensive. $100 per line kilometer would be probably a reasonable price for acquired and processed data. It's actually quite dangerous, and I'll say that every year we learn about some tragedy, and another one happened this year, because in order to get the fidelity of that magnetic signal, the contractors want to fly low, especially if they're carrying gamma ray spectrometers, which have a maximum altitude of about 130 meters in order to not have the gamma ray signal completely absorbed in the water column or the humidity in the air. So helicopters flying with complicated arrays, this again can be dangerous, power lines, mountainous areas. And different types of surveys require different types of aircraft. For instance, particularly those mountain areas almost always require rotary wing aircraft. So these are even more expensive to run than the fixed wing aircraft. However, the acquisition is fast because the fixed wing aircraft is able to travel at 120 knots, and so a lot of area can be covered. So today I want to talk about robotic platforms, and the reason I'm talking about these is that we've developed some new sensors that lend themselves directly to deployment on these types of platforms. So a robot requires, whether it's airborne, marine, or land, requires small, lightweight, low power. Power, of course, becomes range. They're very efficient use of fuel, low operating costs except for the initial investment in the platform. It's obviously safe. Wide range of operating environments, so it doesn't require full airport or air traffic support, for instance, in the remote areas. However, as I said, robotic platforms are range limited. That may be changing now with some sort of aircraft that can be powered from solar. Part of the issues, at least in the United States, are that the FAA controls robotic aircraft in commercial flight airspace. So where we have done some tests and deployed these systems, I have some data, but it's been still under control of the government. So robotic platforms, I just grabbed this, I just typed in robotic vehicles into Google, and this image popped up. Now there are a couple of cars. I bet these are probably Google cars, the ones that drive themselves. But the other ones, you can see there are airborne, there are marine, all sorts of different vehicles that would lend themselves to having a small sensor, perhaps a magnetometer type sensor. So what we've been doing is developing some smaller and smaller sensors, and also concurrently doing research into removing the noise of the platform. Now this is key. If you think about some of those, if I go back here for a second to some of these pictures of aircraft, you'll notice that the sensors are pretty far away from the engines. We try to put them as far as possible. That's the reason you see stingers on these aircraft, because the aircraft makes noise. It makes magnetic noise. So all of these aircraft, however, are compensated. And what that means is that we actually monitor the motion of the aircraft and remove its signature in software. So what we're talking about then is as the platform gets smaller, we get closer to the source of magnetic distortion. Okay, so this requires a more rigorous compensation algorithm, a more rigorous treatment of the data. And so we've been developing not only for yaw, pitch and roll, or heading, pitch and roll motions, and eddy currents, which come from accelerations of conductors through the Earth's magnetic field, like the skin of an aircraft. But perhaps most importantly, we have generated compensation algorithms to remove electrical currents. Why that's important is that most of the robotic vehicles are powered by electric motors. So we have the Sierra UAV from USGS NASA that was done up in Northern California for a geothermal project. I'll show that data. We have the Swift UAV, which will be flying very soon in Nevada. We have the Teledyne Gavia autonomous underwater vehicle, which was a 2-year project that Geometrics entered into with Weston and University of Delaware. That was funded by the Environmental Security Technology Certification Program, ESTCP. We are in discussions right now and have mounted magnetometers on the Kongsberg-Huygen, which is an autonomous underwater vehicle, and a Hydroid Remus is another project. And at the show yesterday, we demonstrated the first commercially available laser-pumped cesium vapor magnetometer. Now, for years, close to 18 years or so, we've been manufacturing cesium vapor magnetometers that are lamp-pumped. A lamp means a fluorescent lamp. In the last couple of years, we've been developing laser pumping, and there are several reasons why this is a dramatic improvement. And I'll go over some of those, but primarily they're smaller, lighter, less power, same sensitivity, and volume production will drive down the price. So compensation software is a crucial component, and we're developing this in conjunction with the hardware. Here's an example of a compensation test. And what we see here is the red line is the raw data. So as the aircraft or the autonomous underwater vehicle rolls, we see a large transient response in the magnetometer, and then there may be some pitching motion, or this may be, I'm not sure exactly whether this say we're going west and we head south, and suddenly we get an offset or heading error due to the vehicle permanent and induced effects. Simultaneously, what I wanted to show here was that when we apply the compensation, we remove the majority of the effect of the orientation of the platform. So we can see that when we have as much as 100 nanoteslas of offset due to the orientation of the aircraft or autonomous underwater vehicle, we can move it into the range of just a few nanotesla. So typically our compensation algorithms can make an improvement ratio of around 20-to-1. So if we can get the aircraft or autonomous vehicle into that range of around 20 nanoteslas of heading error, then we can move it into that sub-nanotesla noise level. We'll also see here some what appear to be random spikes, and this particular aircraft was not compensated for electrical. This was actually done on an unmanned aerial vehicle. This data is from an unmanned aerial vehicle. It comes from one of the large oil companies. So there are a large number of people who are looking at deploying such sensors on a wider range of autonomous robotic aircraft or underwater vehicles. So this was not compensated for electrical interference. We believe this is, we need to have that properly instrumented with an ammeter. And this particular vehicle didn't have that, but we know how to remove this. So here's an example of the aircraft that we used in Northern California with the USGS NASA, and the magnetometer was deployed on the outer wingtip. And here is the Swift, which will be deployed in the next month or so. It's about 80 feet. It's quite long wingspan, and the magnetometer will be placed on the outer wingtip. So here's an example of the data. Essentially, the raw data, the uncompensated data, is on the left, and you can see that there are data pulls. We call them pulls or tears, and they happen because of the aircraft motion is changing the heading error. And then we see what happened when we compensated the data, and the geothermal anomaly associated with this valley is much more clearly delineated. I have another example which is even more clear that was associated with this vehicle. So this is a Teledyne Gavia autonomous underwater robot, and it's been deployed a lot for doing basic sonar search and locating various items of interest on the seafloor. We installed a cesium vapor magnetometer in the nose of this aircraft, of this underwater vehicle. And here's an example of the data. On the left, we see uncompensated data, and this large offset in the data is due to the fact that they recharge the battery. So we actually use an adaptive compensation algorithm to remove the effects of a change in perm in the vehicle itself. And these are unexploded ordnance targets on the seafloor off the coast of Florida. And you can see how once we compensated the data, how much clearer the anomalies are, and especially some are visible that were not even visible in the original uncompensated data. Yesterday at a product demonstration was the first public display of our laser-pumped cesium vapor magnetometer installed on a remotely operated vehicle. So we are in close proximity and doing research together with our friends at Deep Ocean Engineering. And this is their triggerfish ROV. We put an extension boom. Again, we need to get the magnetometer away from the propulsion system, but we do monitor that and remove it. And what the type of applications of a tethered underwater system would be: pipeline location, wreck search, unexploded ordnance, explosive ordnance detection, forensics. The police, FBI, and so forth would like to use this to locate weapons that have been cast into the water, so forth. And of course, intrusion detection. So this would be a homeland security type of device. We call this the Macro-fam. It is laser pumped, as I said, and it's just recently reached production capability, and we're very excited about that. And here's a picture of the device itself. I have another one up here to get an idea of the size. So it has dual lasers, a pump and a probe. One of the things that's interesting about this device is that I showed earlier that in an electromagnetic field that the magnetometer can be knocked off of its line when we use lamps. However, the lasers are much more robust in this, and also they can be placed much closer together. Why is that important? Because we've been doing research recently in making arrays of these magnetometers. And if we can put the magnetometers close together, we can do some sort of automatic target analysis. So we are able to analyze this on the fly using multiple sensors placed closely together. There are also other applications for this type of device, which include biometrics, which means measurement of the human body for magnetic fields. Okay, so I just want to show something about the technology roadmap. We had large sensors. We're moving to MFAM technology. We had large electronics. We are now moving, of course, into integrated circuits to put all of the electronics on a few chips. And then we have multiple sensors that are giving us 2D arrays and real-time processing. So the next step is the MFAM on a chip. We have seen this device operate. We are operating in conjunction with partnerships of people who have wafer fab abilities. And so we will be making the price of the device come way down. And I had a different price at one point. It says 1,000 here at one point, but we believe it'll be even less than that. And if that occurs, then there'll be much more availability of this type of technology for geophysics and other applications, security included. So I'd like to just go to this last slide here. Obviously, this type of development, this type of research, it requires a lot of money, and therefore it's also clear that geophysics is not going to fund this research. And so there are other applications which are actually helping us to devise this tool and make it fully operational at a price that means that not thousands of them, but hundreds of thousands of them can be built. And we believe that this will be available in the next couple of years. So we've got border perimeter type of surveys. We've got ASW. We've got port and harbor security. There are medical applications, for instance, monitoring brain waves. There's IED detection, fences, and geophysics. Thank you very much. Yeah, MFAM stands for Micro-fabricated atomic magnetometer, which means essentially it's built on a chip. Okay. Thank you. Any questions? One question.
Yeah, could you discuss the sensitivity of the MFAM hertz?
Right. Our standard magnetometers are running somewhere between, say, 4 picotesla per square root hertz. We have another system which we're releasing this year, at the end of this year, which will do half a picotesla. The MFAM, we believe, will be in the 10 picotesla range, which means that its noise will be approximately 0.1 nanotesla at 10 hertz. So most maps are contoured at, say, half a nanotesla or a nanotesla. So a 0.1 noise is probably lost in the noise.